Okay, we're going to get started. Technology at its finest. I am your moderator. I am Hope Morgan. Tong Q is actually going to be doing the presentation today. It is on automatic extraction of water bodies from China's ZY3 imagery base. I'm reading this, and a spectral signature. So he is also Herb Stout Award nominee, and on Friday they'll actually be doing that. So y'all should all go vote on lunch on Friday for Tong. And with that, I'll give it to you.
Okay. Hello, everyone. My name is Tom. I'm a PhD candidate in the Department of Geography at UNC Chapel Hill. So today, the presentation will have this 4 different parts. The first one is I'm going to introduce the background and study site. The second one is going to be pre-processing of ZY3 dataset. So ZY is the acronym for resources in Chinese. So ZY just means resources. The third part will be introduced about how to extracting the water bodies using different algorithms. The final part will be designing open source desktop software using Python, C# and ArcGIS engine. Actually, it's not open source because ArcGIS is not free. Yeah, okay. So first, the background. This is a picture of water pollution in the of a side of a river in China. So basically, the water pollution have different sources. First one is the human-made solid materials such as plastic bags or paper that are disposal or abandoned on the side of rivers. So and also monitoring water pollution at large spatial scales is a very urgent issue in China. The second one is increasing water stress in China by catchment. So this is the image from 2001 and 2010 that shows which region, which catchment has increasing water stress. The water stress is defined as the total annual water withdrawals as a percent of the total annual available surface water. So we can see in my study region here in the central China, there's an increasing water stress here from 2001 and 2010. And then about climate change. So on figure A is about the temperature change from 1960 to 2010. So we can see the temperature is significantly increasing. And then figure B shows the trend of precipitation from 1960 to 2010. The precipitation didn't change that much, but however, there's also a decreasing trend. So the temperature is increasing, which means the evaporation is increasing, and the precipitation is decreasing. Therefore, the total input to the water is decreasing. So that's why we should be very careful about the water resources in China. So this figure is only in China, not in other regions in the world. So we can also see there's a seasonal trend here. So in the spring, the precipitation is decreasing. And in autumn, the precipitation is also decreasing. But in the summer and in the winter, we can see an increasing trend. So there's a seasonal difference in the frequency and the amount of precipitation from 1960 to 2010. Here's my study site, which is in the central China, and the Wuhan city. So basically, I select 2 water bodies. The first one is Yangtze River, a part of Yangtze River. The second one is the biggest lake in Wuhan city. And then the object of this study is trying to implementing a water body extraction algorithm and designing a desktop software to help managing water resources. So this study is trying to combine the power of remote sensing algorithm and also the power of GIS to help managing to extract water bodies and help managing the water resources. So let me introduce something about the Chinese ZY3 satellite dataset. So the Chinese ZY3 satellite was launched in 2012, so it's not very new. However, it has a very high spatial resolution, which is 60 meters. And also the temporal resolution is 5 days. So it has both high temporal resolution and also high spatial resolution, which make it a very perfect data source for water body extraction. However, the data we can download from Chinese government website is just raw data, which means, so the raw data is like you are trying to make a Thanksgiving dinner, and then you go to the supermarket such as Harvest Teeter or Whole Foods, you get a raw turkey. So the only thing you can do to frozen raw turkey. So first you have to unfrozen the raw turkey. So just like that, I have to do a pre-processing on the raw data from the ZY3 dataset. So the first part will be pre-processing of the ZY3 satellite data. So the first step is to calculating the top of atmosphere reflectance. The second step is to atmosphere correction. The third part is to image fusion. So calculating the top of atmosphere reflection is a very complicated process, but we can just do them by 3 equations. The first one is imagine that the L, the digital number is the raw turkey. So we are trying to do some transformations to the raw turkey to make it a very delicious dinner. So what we want is the top of atmosphere reflectance, which is ZO, TOA. So we do a set of equations from the digital number. We use gain and bias to get a radiance, the adsense spectral radiance. And then we do a transformation divided by the EBMSI, which is solar irradiance. And then we get the top of atmosphere reflectance. So the DN value is what you can download from the Chinese government website. And then this raw TOA, the top of atmosphere reflectance, is what we want. And then the second step is to atmosphere correction. So the atmosphere correction is we can transform the TOA reflectance, the top of atmosphere reflectance, to surface reflectance. So based on the surface reflectance, we can apply the algorithm to extract the water bodies. So there are currently 2 methods to do the atmosphere correction. The first one is to do a 6S model correction. The second one is a FLAASH model correction. So basically, they have a very similar results, and then there's no significant difference. But the 6S model is open source. So therefore, I can put the model directly into my software, and it can be easily implemented in Python. So the 6S model was selected to do the atmosphere correction. The third part of the pre-processing is to do image fusion. So why we care about image fusion? Because we can combine the 2.1 meter image with the full band 5.6 meters multispectral band. So we can combine the high spatial resolution with the high spectral resolution. I use 3 different methods to do the image fusion. There are 4 figures here. The first one is the original image. The second one is we do a Brovik transformation. The third one is we do a GS transformation. And then the last one is the pan-sharpening transformation. So basically, you cannot see you cannot see judged by the image that this image fusion algorithm is great. So we should do some statistics. So here's the table of the statistics from the image fusion method. The first row is original data. I use 2 statistics. The first one is entropy. The second one is gradient. So entropy is a criteria for how many informations this image can provide to us. The gradient is how we can use the spatial texture of the image to do some like water body extraction. So I also include the 2 statistics for all 4 bands of the image. So we can see the Brovik transformation will lose the information for band 4, which is not good. And the pan-sharpening, the statistics compared to the GS transformation is lower compared to the GS. So the high values is what we want. We want high entropy, high information, and we also want high gradient, which means high contrast in the spatial context. So therefore, I choose the GS transformation to do the image fusion. The final part will be do the water body extraction algorithm. So this algorithm is very easy and very just 4 steps. The first one is to do a band math. We calculate the NDWI and then normalize the difference water index, and then we do the CIWI, which is combined index of NDVI and also NRR. And then we do a normalized difference soil index, NDSI. So they are all widely used the remote sensing index. And then from those three index, we do a PCA transformation, which is a principal component analysis transformation. The PCA will generate the first principal component, which can use all the information provided by the three water index. Here is the results from the three different water index. So we have two study regions. So therefore, the NDWI, where the color of water is more black, and then the CIWI, which is the combined index of NEVI and NRR, where the water is more like has white color, and then the NDSI, where we cannot judge where the water is, but however it can provide some information that human eyes cannot catch. Similarly, for the study region 2, we can also see the black water bodies here, the white water bodies from here, and also we cannot see a clear difference, but it's more like a light gray, a dark gray here for the water bodies. The next step is to do a PCA, a principal component analysis. So the PCA is like so we have three index here. So, but we only have one image for the water bodies. So how can we combine all the information we have from the different water index and then extract the water bodies? It's doing a PCA. So the PCA, after the PCA transformation, so this is the band combination using the three water index. And then the second one is after we do the PCA, we have the first component, the first principal component. And then this figure is the histogram. So based on the histogram, we can see the water bodies has a significant difference histogram compared to the other land covers. So we can easily choose a threshold from here to separate waters from other land covers. So similarly, in study region 2, we can also do a histogram and then separate the water bodies based on the histogram using a threshold. And here's the results when we do we even use a threshold to separate the water bodies. In this, it's a binary image where the white regions means non-water body. The black regions means water bodies. So the algorithm works really well at extracting the water bodies, even if the algorithm is very easy. So they are very thin water bodies here, but it can also extract the water bodies very accurately. The second study regions also, we can see the boundaries of the water layers is very, we can see a very detailed water boundaries from this figure. And then we can do the accuracy assessment using different random points and using human eyes to determine if it's a water body or not. So this is a result from the producer accuracy, the user accuracy, and total accuracy. So that accuracy can be as high as 90%, which is very good, even if the algorithm is very simple. So the next step is we try to combine the algorithm I use and then use ArcGIS engine and C# to design a GUI to help the government to do the water management. So this is the workflow of how I combine the Python algorithm and the C# COM component and also ArcGIS engine to design this desktop. So basically, I write all the algorithm in Python. Then I compile the algorithms into different modules, and then use C# to design the GUI, and then use ArcGIS engine to help design the GUI, and then run the desktop. So here is some screenshot of this software. So this software has 5 components. The first component is that we can visualize the image. The second component is we can pre-processing the image. And then the third component is we can do a band math to calculate the water index. And then we can do a PCA analysis. And the final part is to do a threshold analysis. So as I mentioned earlier, the atmosphere correction includes, first we calculate the TOA reflectance, and then we do a atmosphere correction to transform the TOA reflectance to surface reflectance, and then we do the band mass to calculate water index, And then we do a PCA and a thresholding to extract the water bodies. This is a figure. This is a screenshot of combining C# and ArcGIS engine. Therefore, we can visualize the image using a one band, a gray band, or a multi-band RGB to visualize the image. So this is the band combination is from band 1, band 2, and band 3. On the left corner, you can see there's the eagle view. So you can use this eagle view to zoom up the image if you want. And then the next step is for the TOA reflectance calculation. Those figures are generated from the Chinese government website. So we import the data as CSV to this software, and we can generate this at sensor spectral response. Then we can calculate the TOA. This one is about so we can do as I mentioned earlier, to calculate TOA you have to have an EMBI, which is the solar radiance. So the solar radiance information, which is not available. So we have to calculate them from the website. And then this is the band math. Where we can use this a different band math, such as band 4 minus band 2 divided by the band 4 plus band 2. So the NDWI, CIWI, and also the SDVI, the NDSI is also based on this band combination. And then we can do a PCA transformation where you input the 3 water index, NDWI, NDSI, and also CIWI, and then you generate a PCA first component. And then you can do a thresholding based on the threshold you give. So here I use 125. And the final part will be we can do an accuracy assessment. You can generate random points over the study regions and decide if this is a water body or vegetation. For example, here, some points are in the water bodies, so some are not. So the red arrows shows a bunch of pixels that are vegetation, and those arrows shows the land cover is waters. So basically, you can use the human eyes to judge if it is a water body or not, and then you can compare with the algorithm generate water bodies to get the accuracy of this algorithm. The future directions will be releasing the software to the water management authorities and the general public, and then the second direction will be combining spatial textures. So in this study, we use a very simple algorithm, which is based on just the spectral information. But here we are going to combine spatial texture and spectral information to better extract water bodies. Yeah, that'll be all. Any questions?
So fast.
Oh, yeah, that's right.
I actually have a question. How quickly can this be run?
How quickly? Wow, that's a very good question. So normally, so this software is written in Python. So Python is not a very fast software. So basically, for this image is about 5,000 pixels multiplied by 4,000 pixels. Gonna run like 1 hour to get the water bodies.
Okay.
Yeah. Yeah. Yes. Yeah, I plan to, but the ArcGIS engine is not free, so they are not allowing me to upload them. Yeah, but I'm gonna compile them to a software and put it on the GitHub. Yeah, definitely. Yeah.
I think you can also work with Esri to
get
your pieces of it provided.
That's right, like a standalone software. Yeah. Any other questions? Okay, perfect.
Quite amazing. Thank you very much.